This video cassette displays sequences of satellite imagery portraying atmospheric phenomena. The events depicted provide a view from space of the circulation of weather systems on Earth and other planets. The images also provide insight into spatial and temporal scales of atmospheric motion. The first sequence of imagery shows the cloud patterns over the Western Hemisphere on November 20th, 1980. A single visible and infrared image from noon Eastern Standard Time is followed by sequences of imagery. In the mid-latitudes of both hemispheres, clouds associated with extratropical cyclones are located over the Atlantic and Pacific Oceans. A large region of low clouds is present over the subtropical Eastern Pacific Ocean, associated with relatively cold ocean temperatures. Daytime surface heating over the Amazon basin of South America produces convective clouds. The infrared imagery indicates cold high-level clouds, the brightest regions, warmer mid to low-level clouds, the gray regions, and cloud-free areas, usually the darkest regions. High clouds associated with rising motion, either along frontal boundaries or with deep convection, are the most evident features in this image. In the sequence of visible imagery, the most evident feature is the movement of the day-night terminator across the Western Hemisphere. The orientation of the terminator indicates it is summer in the Southern Hemisphere and winter in the Northern Hemisphere. Convective cloud formation increases over the Amazon basin in the afternoon, leading to thunderstorm development. Due to the effects of the Earth's rotation, or the Coriolis force, mid-latitude cyclones rotate counterclockwise in the Northern Hemisphere and clockwise in the Southern Hemisphere. A continuous band of clouds just north of the equator stretches westward across the Atlantic Ocean over the northern portion of South America to a large cloud mass in the tropical Pacific. This band of clouds represents the position of the intertropical convergence zone. In the sequence of infrared images, the development of convective clouds over South America is more evident. Individual thunderstorms grow during the afternoon, producing cirrus outflow, which rotates anticyclonically or counterclockwise in the Southern Hemisphere. The expansive medium gray region covering much of the South Pacific Ocean indicates the presence of stratocumulus clouds associated with relatively cold sea surface temperatures. There is little movement of this cloud mass. The brightest areas in the band of cloudiness along the intertropical convergence zone indicates regions of strongest convection. Notice that in most subtropical areas, the low-level easterly trade winds are overlain by upper-level westerly winds. Just north of the equator in the Pacific Ocean, the movement of the large bright cloud mass indicates an interaction between warm, moist tropical air and the cooler, drier air of the mid-latitudes. Embedded in the westerly winds of the mid-latitudes, cyclones transport warm air poleward and cold air equatorward. An occluded cyclone over the North Atlantic Ocean has a wave or second cyclone developing along its frontal boundary. Finally, medium gray shading over much of the Atlantic Ocean indicates stratocumulus clouds behind this front, associated with cold air and warm ocean temperatures. Moving to the synoptic scale, the next sequence of images portrays the rapid intensification of a mid-latitude cyclone and associated line of severe weather-producing thunderstorms in the central United States. The cloud mass in eastern Nebraska and western Iowa indicates the position of the developing low-pressure system. During the day, the center of the low moves to eastern Iowa. Morning thunderstorms in eastern Kansas spread into Missouri, while numerous thunderstorms develop along a line stretching from Illinois to Texas. The medium gray portion of the imagery in the lower Mississippi River Valley indicates low cloudiness and fog in the warm, moist air east of the cyclone. As the thunderstorms develop, large amounts of cirrus clouds are produced, indicated by the large, bright, white region ahead of the squall line. Speeding up the image sequence can help to provide a better overall visualization of the cloud motions within a cyclone. Note the cyclonic spin near the center of the storm. The contrast of warm, moist air and cold, dry air creates moisture and temperature gradients to aid in thunderstorm development. By color-coding the infrared brightness values, relative cloud heights can be differentiated. The black color depicts the warmest regions, usually cloud-free or very low cloud areas, while progressively higher clouds or colder surface temperatures are indicated by the colors blue, green, red, and white. Notice that as the squall line intensifies, the colors turn from green to red and finally white in the most intense areas of convection. Visible imagery shows more distinctly the broad area of low clouds and fog in the lower Mississippi River Valley. Southwest of the squall line, thin lines of towering cumulus precede cumulonimbus cloud development. The textured appearance of thunderstorm cells makes it easy to locate the squall line along the western edge of the expansive area of cirrus cloud blow-off. Cold, dry, subsiding air moves in behind the squall line, leading to rapidly clearing skies. A tongue of dry, subsiding air moves northeastward through Missouri into the upper Midwest, indicating the presence of a strong upper tropospheric jet streak. Next, two regions through which the squall line passes are examined in higher resolution imagery. The yellow box locates the region that will be shown. Because the higher resolution imagery contains a smaller spatial area, the images appear to jump more. Wave patterns and thin cirrus clouds give way to thicker clouds and the coarsely textured appearance of thunderstorm cells. In higher resolution imagery, the squall line no longer looks continuous. Numerous individual cells can be discerned, separated by areas of less intense activity. The last images show a second, less intense line of thunderstorms moving into the area. The second high-resolution sequence covers most of Arkansas and part of Mississippi. In the upper middle portion of the first image, the peaks of the Ozark Mountains rise above the low clouds and fog. Again, wave patterns and cirrus clouds precede the thunderstorms. As the thunderstorms develop, the regions of most intense convection form cumulonimbus towers, which cast shadows on lower clouds in the late afternoon. Mid-latitude cyclones pass through life cycle stages which include development, maturity, and occlusion. This East Coast storm develops along a strong temperature gradient of cold continental air and warm moist air over the Gulf Stream. Moist onshore flow is being lifted over Virginia and North Carolina, creating an expansive cloud mass. The presence of an upper tropospheric jet streak is again suggested by the clear tongue moving northeastward along the coast. Just ahead of the jet streak, a thick cloud layer produces heavy snow along the east coast of North Carolina. The cold front is located along the line of convection stretching southwestward across Florida. Stratocumulus clouds form off the South Carolina coast in response to cold continental air moving offshore. Cloud motions in the infrared suggest a deep trough in the upper atmosphere over the eastern United States. Northerly flow is present over the upper Midwest, turning to the west over the southeastern states, and finally to the southwest along the Atlantic seaboard to New England. It is over the eastern edge of this upper air trough where the advections of cold dry air and warm moist air create the temperature and moisture contrast important to cyclogenesis. Enhancing the infrared imagery makes identification of mid and upper level clouds easier. As the cyclone develops, the broad area of higher clouds expands and moves offshore. An occluded springtime cyclone is almost stationary over eastern Illinois in the next sequence of images. The merging of warm and cold fronts produces a rotating pool of cold air at the surface, with the upper air trough located directly above the surface low. Infrared and enhanced infrared imagery indicates the highest clouds are north and west of the cyclone center. This storm produced a band of snow which accumulated 2 to 4 inches from Wisconsin to Missouri. Through the snow band, the meanders of the Mississippi and Illinois rivers are apparent. Above freezing temperatures rapidly melt the snow. These sequences portray Hurricane Allen as it moves through the Caribbean Sea and Gulf of Mexico. The eye of the hurricane is easily located just south of the Dominican Republic as the storm moves westward. Heavy thunderstorms encircle the eye and form bands which spiral inward toward the storm's center. The hurricane's low-level circulation is cyclonic, while the upper-level outflow is anticyclonic, characteristic of a warm core cyclone. 30 hours later, near the western tip of Cuba, Hurricane Allen began to intensify rapidly. Strong upper-level divergence or outflow is suggested by cirrus clouds moving away from the hurricane. Brightening of the images near the storm center and the distinct eye definition indicates Allen's strengthening. "12 hours later, as Hurricane Allen entered the Yucatan Channel between Mexico and Cuba, the central pressure of the storm reached 899 millibars, the second lowest pressure ever recorded in an Atlantic hurricane. High-resolution imagery indicates an extremely well-formed eye. The funnel shape of the eye is found only in the most intense hurricanes. Late that afternoon, Allen entered the Gulf of Mexico. This single image, shown at 3 resolutions, provides insight into the scale size of the hurricane. A larger mid-latitude cyclone is located near Greenland, while smaller thunderstorm clusters are located in the upper Midwest of the United States. Tropical cyclone Isis is located west of Mexico. The diameter of Hurricane Allen's cloud cover is approximately 900 kilometers, although hurricane-force winds occur only in a small region near the storm center. This sequence of visible imagery begins with the single frame just shown. Feeder bands to the south and east of the hurricane supply moisture to feed its circulation. Developing thunderstorms within the bands indicate instability in the converging air. Passing north of the Yucatan Peninsula, Allen's circulation drew in much drier air off the landmass and went into a period of weakening. In the infrared sequence, darker shaded bands in the grayscale, which spiral in toward the center of the hurricane, indicate much drier air is being drawn into its circulation. The result is reduced thunderstorm intensity and a loss of eye wall definition. Thus, losing a portion of the latent heat energy needed to drive its circulation, Hurricane Allen's central pressure rose 60 millibars. Notice, however, that strong upper-level divergence is still present over the region. The enhanced infrared imagery portrays the differences in cloud heights more distinctly. The rapid decrease in intensity of the thunderstorms forming the eye wall, the white area, and the drier air being drawn into the circulation, the blue bands, provides convincing evidence for the weakening of the hurricane. The final sequence depicts Hurricane Allen 24 hours later as it approached the Texas coastline. Allen had again intensified as it moved across the Gulf of Mexico. However, its forward speed now began to decrease, and the hurricane weakened as it crossed the Texas coastline 24 hours later. Enhanced infrared imagery indicates heavy thunderstorm clusters embedded in the circulation moving onto the Texas coast. Moving next to smaller spatial and temporal scales, this sequence of imagery shows the effects of solar radiation on a convectively unstable atmosphere. The cloud motions indicate the presence of an anticyclone off the southeastern coast of the United States and a cold front with a developing wave moving through the upper Midwest. In this early afternoon period of 3 hours, numerous cumulus clouds form in the southern states, some developing into thunderstorms. Along the eastern shore of Florida, surface convergence caused by a sea breeze creates a line of cumulus. Also included in smaller than synoptic scale dimensions are squall lines and individual thunderstorms. The tornado-producing thunderstorm that devastated Wichita Falls, Texas, has been studied extensively by meteorologists. The crosshair indicates the location of Wichita Falls. In the late afternoon, several very intense thunderstorms develop and move northeastward between a strong moisture gradient and warm front. The particular thunderstorm under study is the last to develop and is located closest to the Gulf of Mexico. Note the cloud of dust moving into the Texas Panhandle as strong, dry westerly winds behind the front blow across parched land, carrying away topsoil. On this day, a special network of surface and radiosonde stations was in operation. The sensors on board the geosynchronous satellite scanned the central United States at 3-minute intervals instead of scanning the full Earth disk at 30-minute intervals, thus providing a significant increase in temporal resolution. Using the highest spatial resolution possible, scientists were able to obtain an extremely valuable sequence of satellite imagery. The textured appearance of clouds embedded in the vast amount of cirrus outflow or blow-off locates the areas of most intense convection. The black spot east of the cumulonimbus cloud moving toward Wichita Falls is probably a shadow cast by an overshooting cumulonimbus tower. The tornado on the surface is located in the vicinity of this tower. This series of 3 still images depicting progressively greater resolution displays cloud formations associated with cold, dry air moving over a warm sea surface. The purple box outlines the area included in the following image. A strong surface anticyclone is moving over the Gulf of Mexico. The sensible heat transfer from water to air leads to buoyant parcels rising, mixing with, and condensing in the cold, dry air above the surface. Strong winds aloft arrange the clouds in rows or streets parallel to the wind field. The clear areas between the streets are due to subsidence compensating for the rising motion. During a very hot, dry spring, a number of forest fires occurred in the upper Midwest. This fire began near Spooner, Wisconsin. Clouds over eastern Wisconsin in the first images are associated with a weak cold front. As the smoke plume rose, it encountered more westerly winds in the upper atmosphere, causing the plume to appear to curl. It is possible that periods of greater fire intensity created more intense thermal plumes, which rose to greater heights and encountered the southwesterly winds. Shadows cast by the plume suggest height variations within it. Plumes of this type are studied to better understand the dispersion of atmospheric pollutants. The geosynchronous satellite over the eastern Pacific Ocean provides a view from space of the dramatic eruption of Mount St. Helens. The eruption occurred on a Sunday morning at 8:38 a.m. Pacific Daylight Time. Clouds associated with a weak cold front are moving onshore, while high pressure dominates eastern Washington and Oregon. The debris cloud quickly reaches the tropopause, about 12 kilometers, and spreads eastward in relatively weak upper tropospheric westerlies. Measurements indicate the leading edge of the debris cloud is moving at approximately 20 to 25 meters per second, or 40 to 50 miles per hour. The anticyclonic curvature of the debris cloud indicates it is being carried over a weak upper air ridge. color enhancement of the infrared brightness temperatures separates the eruption plume from clouds associated with the cold front. This enables more accurate measurements of the debris cloud to be obtained. The shape of the debris cloud possibly verifies the fact that the initial major eruption was followed by a series of less intense but more continuous eruptions. Beneath the ash and debris cloud, visibilities were greatly reduced. Less than 8 hours later, most of eastern Washington had visibilities less than 1 kilometer. This ash fallout moved into northern Idaho and western Montana shortly thereafter. Total ash deposits reached 5 to 10 centimeters over much of eastern Washington. A series of 4 high-resolution visible images capture the dramatic period of the initial eruption. The initial eruption is actually an intense explosion. The second image is approximately 10 minutes after the eruption. White cirrus clouds associated with an intense shock or gravity wave are visible moving away from the volcano in all directions. The shape of the debris cloud shortly after the eruption has been compared to the anvil of a mature thunderstorm. Note the distinct shadows cast on the Earth's surface west of the plume by the debris cloud. The next portion of the video cassette provides sequences of imagery of the planets Venus, Earth, Jupiter, and Saturn. The Venus imagery was obtained from the Mariner flyby mission, which approached the planet in February 1974. Venus is covered by a very thick layer of clouds, composed mainly of carbon dioxide. The abundance of carbon dioxide has created a greenhouse effect, trapping solar energy in the atmosphere and raising surface temperatures to 450 degrees Celsius. The bright vortex about the South Pole is thought to be a region of stratospheric convergence and thus subsidence. Researchers believe the brighter equatorial regions are examples of convection on Venus. The westward propagation of the dark Y-shaped feature across the equatorial region of the stratosphere is moving at 100 meters per second. This sequence of imagery of Earth, also shown at the beginning of this tape, provides a comparison and contrast to the circulation of the other planets. A notable difference is the partial cloud cover on Earth, enabling a view of the planet's surface. The seasonal cycle of the Earth, due to the tilt of its axis, causes changes in the general circulation of its atmosphere. This sequence is from the northern hemisphere fall and southern hemisphere spring. A generally westerly flow of clouds is present in the mid and high latitudes, while convection seems to dominate the equatorial region. In the subtropics, weak upper-level westerly winds overlie easterly trade winds near the surface. These images were sent back to Earth by the Voyager 1 spacecraft as it approached Jupiter in February 1979. We wish to thank the Jet Propulsion Laboratory for this sequence and also that of Saturn. The most evident features in this sequence of images are the different colored bands encircling the planet and the great storm in the southern hemisphere. The cloud motions within the belts indicate a large variation in wind speed and direction at the top of the Jovian cloud layer. Wind speeds vary from near 130 meters per second near the equator to 0 at the poles. Clouds moving in different directions along belt edges indicate the presence of a strong horizontal wind shear. Along these shear zones, turbulent eddies form. The largest and most striking of these eddies is the Great Red Spot, featured in the higher resolution imagery. The Great Red Spot is an anticyclonic storm with a diameter of 25,000 kilometers. Note the westward moving current to the north of the storm and the eastward moving current to the south. A tremendous amount of turbulence is generated between these belts and the Great Red Spot. Smaller colored white storms enter the circulation of the Great Red Spot and are significantly altered. This imagery of the planet Saturn was sent back to Earth by the Voyager 2 spacecraft in July 1981. As with the planet Jupiter, numerous different colored zonal cloud belts encircle the planet, creating similar patterns of turbulence. Cloud motions indicate equatorial wind speeds near 500 meters per second. Wind speeds initially decrease away from the equator, but then increase again to a second maximum of 100 meters per second near 40 degrees latitude. Oval-shaped storms or vortices are also present along belt boundaries. Finally, notice the spokes or dark spots in the rapidly rotating ring system of Saturn.